Welcome to the video lecture series on Chemical Engineering Thermodynamics 1. Myself, Jaimin Pandya, Assistant Professor in Chemical Engineering Department of LJIET Institute of Engineering and Technology. So let's continue with the previous chapter, which is a heat effect. So in this lecture, we'll talk about approximate method for the estimation of latent heat of vaporization, and then talk about the effect of temperature on heat of reaction, or we can say that temperature dependency of heat of reaction. So let's continue with approximate method for estimation of latent heat of vaporization. So what is meaning of latent heat? Latent heat, which means heat required to change the phase of any substance at constant temperature, is known as the latent heat. The latent heat during the phase change is function of temperature only and is related to the other system property by the exact thermodynamic equation that can be given by delta H is equal to temperature into change in volume into dP saturated upon dt. So this equation given by the change in enthalpy is equal to temperature into change in volume into dP upon dt, where T is equal to temperature, delta H, which means latent heat, or can say that enthalpy change during the phase change, then delta V, which means volume change during the phase change, and Psat is saturated pressure, which means pressure at which phase change occurs, which is a function of temperature. The derivation of this equation is known as the Clapeyron equation. So this method is also known as the Clapeyron method. So we can find out heat of vaporization using this equation with help of various data such as temperature, change in volume and saturated pressure. Using this data we can find out latent heat of vaporization for any particular system. So now let's talk about one another method, which is a Watson method. Watson method, which used for estimation of latent heat of vaporization of pure liquid at any temperature from non-value of single temperature. So this method is known as the Watson method. Watson equation that can be given by delta H2 upon delta H1 is equal to 1 minus Tr2 upon 1 minus Tr1 whole raised to 0.38, where Tr is a reduced temperature at particular temperature. In thermodynamic, reduced property of fluid, which means a set of state variable scaled by the fluid state property at critical point, which means actual property divided by the critical property. So if we want to find out reduced temperature, so it can be given by actual temperature of particular substance divided by critical temperature of that particular substance. So with help of this equation we can find out latent heat of vaporization. To understand this, let's take one example. The latent heat of vaporization of water at 100 degrees Celsius is 2257 joule per gram. The estimate the latent heat at 300 degrees Celsius critical temperature of water, which is a 647.1 Kelvin. So in this numerical given that latent heat of vaporization at 100 degrees Celsius, which is a 2257 joule per gram, and told that find out the latent heat at 300 degrees Celsius. Given that critical temperature of water is 647.1 Kelvin. So using this Watson equation easily calculate latent heat of vaporization. So let's calculate the latent heat of vaporization. Let delta H1, which is a latent heat at 100 degrees Celsius, which already given in statement, which is a 2257 joule per gram. Let's consider delta H2, which is a latent heat at 300 degrees Celsius, which we have to calculate. Then first we have to find out this Tr2 and Tr1. Tr1, which means reduced temperature 1, reduced temperature at 100 degrees Celsius, reduced temperature, which means actual temperature upon critical temperature. So what is actual temperature? Actual temperature, which is 100 degrees Celsius. Now if we are going to converting this degree Celsius into the Kelvin, then we have to add 273.15. So by adding 273.15 in this 100, we'll get 373.15 Kelvin divided by critical temperature of water, that can be given by 647.1 Kelvin. By calculating this term, we'll get 0.577. Similarly, can calculate reduced temperature at 300 degree Celsius. So reduced temperature, which means actual temperature upon critical temperature, actual temperature which is 300 degree Celsius, 300 plus 273.15, that can be given by 573.15 upon critical temperature of water, that can be given by 647.1. By calculating this term, we'll get 0.886. So using this both value in this equation, we'll get this term. So using this delta H1 value, which is 2257. So let's put this value at, let's take this delta H1 to here and put the value of delta H1, then TR2, value of TR2, which is 0.886. So let's put that value. Then TR1, value of TR1, that can be given by 0.557. So let's put value of TR1 0.557 whole raised to 0.38. By calculating this term, we'll get this term, and calculating this whole term, we'll get 1371 joule per gram, which is the heat of vaporization at 300 degrees Celsius. So it is the answer of heat of vaporization of water at 300 degrees Celsius temperature. So this is the Watson method to find out latent heat of vaporization. Now let's talk about the temperature dependency of heat of reaction. In previous lecture, standard heat of reaction were discussed for the arbitrary reference temperature of 298.15 Kelvin temperature. In this section, we treat the calculation of standard heat of reaction at other temperature from knowledge value at the reference temperature. To understand this, let's consider this diagram or this figure. In industry or in actual, reaction occurs at temperature T, for which the standard heat of reaction delta H is maybe treated as occurring 3 steps. So in actual, it is not possible that all the reaction which occurs at 298.15 degree Kelvin temperature. So it is necessary to find out the heat of reaction at different temperature. To understand this, let's consider this figure. In this figure, given that reactant at temperature T and reaction occurs and produce the product at temperature T. But this is a temperature 298.15 Kelvin. As said previously, it is not possible to all the reaction occurs at 298.15 Kelvin temperature. If some reaction occurs at different than 298.15 degree Kelvin temperature, then we have to calculate in 3 steps delta H, such as a delta H for the reactant, then delta H for the reaction occurs, and delta H for the product. So let's consider this figure. In this figure, reaction occurs at 298.15 degree Kelvin temperature. Now, if we consider or if we assume the reaction temperature is different than 298.15 Kelvin, let's assume the reaction temperature is lower than 298.15 Kelvin temperature. Then first step, we have to consider reactant is cooled down from 298.15 Kelvin temperature to the actual temperature of that reaction. Then reaction occurs at that temperature, and then again product occurs or product produced at that temperature, and again this product is formed or this product is achieved at 298.15 degree Kelvin temperature. So using this can easily calculate the heat of reaction for other temperature. So for that, total heat of reaction, that can be given by delta H1 plus delta H2 plus delta H3. The reactant are cooled from the temperature T to T1. The enthalpy change for this step, that can be given by delta H1 is equal to summation of integration of T to T1 and Cp dt, which is our enthalpy change equation, and Cp delta T. Now if we want to write this equation in term of stoichiometric number, then we have to write minus Vi Cp dt. If taking this minus into this side, then it becomes T1 to T Vi Cp dt, where Vi is a stoichiometric number. Stoichiometric number for reactant is always negative. That's why we take minus here and change the limit from T to T1 to T1 to T. So we are changing limit from T to T1 to T1 to T because stoichiometric number for reactant is always negative. So if we take this negative sign in this integration, so we have to change the limit from T to T1 to T1 to T. That's why this equation becomes summation of integration of T1 to T VICP dt, where Vi is the stoichiometric number of reaction. Then second step, which is a reaction occurs at particular temperature, enthalpy change for that temperature that can be given by delta H2 is equal to heat of reaction for that temperature. And third step, which is a temperature of product rise T1 to T, the enthalpy change for this step is delta H3 is equal to summation of integration of T1 to T and Cp delta T. Here take T1 to T because in previous slides seen that the temperature is rise from T1 temperature to T temperature. That's why here we take T1 to T. So Ncp delta T. If we want to write this equation in term of stoichiometric number, then N is replaced by the stoichiometric number, and stoichiometric number for the product is a positive, so there is no change in this limit. In here we take limit T to T1 because in this figure can see that temperature is changed from T to T1. That's why here we take limit of integration is T to T1. Using this all three terms in equation, we will get delta Ht is equal to delta H1 plus delta H2 plus delta H3. Summation of this all three terms will get this term. By summating these two terms, we will get delta H0 plus integration of T1T into summation of VICP dt. These both terms are same, so we can write integration of T1 to T summation of VICP into dt. VICP is equal to delta Cp. So can write this equation delta H0 T is equal to delta H0 upon T1 integration of T1 to T delta Cp dt. So using this value of Cp in this equation and integrating from T1 to T temperature, we'll get delta H0 is equal to delta H0 T1 plus delta alpha into T minus T1 plus 1 by 2 delta beta T square minus T1 plus 1 by 3 delta gamma T cube minus T1. If we want to write for single temperature, or if we want to measure enthalpy change for the single temperature, then this equation becomes like this: delta H0 is equal to delta H dash plus delta alpha T plus delta beta upon 2 into T square plus delta gamma upon 3 T cube. So this is the equation of temperature dependency of heat of reaction, or effect of temperature on heat of reaction. So using this equation can calculate heat of reaction at particular temperature T. So this is all about this lecture. I am completing my lecture here. Thank you.